Good afternoon, everyone. I'm Daniel Sobien. I'm a research associate at Virginia Tech's National Security Institute. I do a lot of stuff around computer vision, data fusion, data augmentation for that. That's what I want to talk a little bit about today, the impact of data quality issues on computer vision, data fusion models. So this is data fusion is just combining disparate sources of data. We've even used it for decision fusion, so combining outputs from different models together. Sort of the context of the problem I want to focus on today is how do we work with smaller data sets? So we have limited sizes. This can be from data sets that might be more difficult to collect. So things like synthetic aperture radar. There's not a whole lot of it kind of available for training, or situations where we might have satellite imagery that takes expertise and time to kind of label all the things within it. Um, there are kind of workarounds to deal with these. We can simulate things like SAR using physics-based simulations, but then there's kind of this simulated to real gap that needs to be kind of crossed um, for having limited data in general. It can be just difficult to deal with. And so one of the things that we've looked at in the past is how we might use data fusion to kind of address these issues. We've ran into some data quality issues or like have sort of discovered some data quality issues in the work that we've done in the past. Um, One of these has been synthetic aperture radar. So we have used physics-based simulation to model surface ship wakes using hydrodynamic simulation, and then feeding that into a SAR model using different SAR bands. So basically, this takes a lot of expertise and time and compute and having supercomputer clusters. But we can get some data to start working with. We were able to simulate three different bands. So we have the C band, S band, X band. Um, those are just different frequencies of radar. They kind of have different features. You can see, um, you know, these are different scenarios between them, but you can kind of see different characteristics between the two. Some have more noise, some have less noise. Um, and these are all still pretty simplistic. So compared to real world data on the left, here this is from the Copernicus Sentinel-1 satellite. There's a couple different ships near this harbor, and you can see the wakes are a lot smaller. There's some movement in them. There's multiple ships, whereas the stuff that we've kind of been simulating to start with is a lot more simplified. This has been a more of a proof of concept, but we've also been using data augmentations to kind of add some of this variation and deal with these issues. Right. So the big issue is how do we train a model that's going to generalize to some of those real world conditions? And what we've done in past work is using data augmentations to mimic sets of real world conditions. There are two I want to focus on today. The first is speckle noise, and the other is zooming out, so changing the size of the wake within the image. And then the idea is that we would implement data fusion. So we would combine the different SAR bands together with the hope that they would improve performance, or at least when we see out of domain scenarios, situations and features, that the data fusion would help sort of lessen the impact from the out of domain data and the variations. So just a quick example of the two different data augmentations that we used. The top here is speckle noise. Basically, it's kind of what it looked like before, but a little grainier. The bottom is zoom out. Right, so that the wake size shrinks a little bit. The zoom out isn't too radical, and we mirrored the edges a little bit too, so we're not creating like weird boundaries, removing any of the background. A quick overview of the deep learning models. So this was a really simple baseline classifier, just a CNN model with three convolutional layers and two fully connected layers. The data fusion we did is a form called decision fusion, where we take the output from the different baseline models and combine them together. We did a Bayesian fusion, basically just a Bayesian update, using validation results on validation data as the prior. The second is Dempster-Shafer fusion, which is basically a information theory. And we take the output of the different models as a belief and then combine those beliefs to get an updated belief on what's going on in the image. So some of the results. The different lines, this top line is the C-band benchmark data. So all models are trained on the clean data, and then the benchmark values, these lines are tested on clean data as well. And then we've tested those models on some of the augmented, the out-of-domain data to see how performance changes. The C-band and X-band on speckle noise do basically about the same. There's not much of an impact. There is a large impact on the S-band model performance. And we see that kind of crossover into the data fusion, the ones here kind of on the right. We combined CS and X bands, S and X bands, and C and X bands. Basically, ones where we used S band kind of have the most impact to performance. With the zoom out, we see kind of similar degradation. It's a little more intense. So S band does really poorly with this augmentation, and this kind of bleeds over to all of the data fusion models that use them. Right. So what we're kind of seeing here is that while S-band might do okay with data that's in domain to the training, when we sort of start to move out of domain, there's a much larger impact. And we might think that, oh, we can just sort of combine these different data sources together. The model will figure out what to do. Well, when we're getting in situations we haven't seen before, like that impact to the S-band can then like propagate within the decision fusion model and kind of like give us worse performance than we would expect or would like. And so I think that doing test and evaluation, sort of understanding how well your model performs on the different sources, sort of testing the boundaries of where the model performs well is really needed. So you understand sort of what's going on and maybe what conditions that you can test this in or feel confident that your model is going to perform in. So the second scenario I wanted to cover is looking at satellite imagery, where we might not have a lot of data because it's difficult to label. So for another project, which we also use data fusion on, we use the SpaceNet 8 data set. So this is a data set, a segmented data set trying to identify buildings and roads in an image and then identify which have been impacted by a flooding event. And so the data set consists of paired pre-flood and post-flood images. And basically both of these are fed into a model, and then the output gives segmentations of where the buildings and roads are and if they are flooded or non-flooded. So this data set, there's only about 800 labeled images in the whole data set, which isn't really a lot for computer vision. Of those, about 70% of them don't have any flooding going on in them. So that makes the problem of identifying, which features are flooded a little more difficult, because the features are small, especially roads are small within the images. This can make it really challenging. So we can't really rely on small models. We need some more complexity. But then the limited data set makes this harder to train bigger models on. We used UNet and YOLO based models. UNet did pretty well. the YOLO model struggled, even with a small uh, YOLO V8 model. It had a lot of difficulty. Um, and so one of the ways we address this, and I'll get into this a little more, is that we implemented a discount factor to sort of weight based on the model's validation performance. Um, so just another quick overview of the different models that we used within the study. The first one is top left. This is the SpaceNet 8 baseline. That's from the people who released the data sets. This one is UNet based. The one below it, this NewNet, that's another open source model that we took and we adapted it a little bit, but it's a nested UNet. So basically sort of similar to the SpaceNet 8, but instead of having the large gaps between the different layers, we're kind of filling them in. And then it has some attention modules in there as well. The top right is just a YOLO segmentation model. So it's kind of in the style of YOLO families, and it's basically an object detection model that then has some segmentation heads added to it. And like the work I was talking about earlier, we also implemented decision fusion. This one focuses on just Dempster-Schaefer decision fusion to combine outputs from two different models and also looking at the uncertainty. So some of the results, here I have some of the Matthews correlation coefficient results for the different models. The SpaceNet 8 baseline model did the best. I kind of suspect because it's the simplest and the data set isn't terribly large that it did well. The next best one is the SNUNet. The YOLO model did pretty poorly. It was a lot worse than I expected. So one of the issues with then trying to do data fusion, decision fusion on this YOLO model is that, if you have like a really big gap between performance of two models you're trying to combine, or maybe a big gap between quality of data sources that you're trying to combine, you don't necessarily always see an improvement. You might sort of get this averaging effect when you're combining them. So one of the ways we addressed this in the study was to use a discount factor. And so we tested the models on, or we used the models on validation data. And then based on their performance on validation data, we weight the outputs from the different models. It's a little more complicated than that. Basically, the discount factor is used as an uncertainty during the Dempster-Schaefer fusion. And so we combine it with that additional uncertainty. And then what we see when we add a discount factor is that the baseline plus the YOLO model with the discount factor basically doesn't have any degradation, and the baseline with the SNUNet model that has a validation or the discount factor, we see a very marginal improvement, which it's promising. I think having more data would obviously help these models improve a little bit more. But I think showing that, testing the models that you do have, being able to say, I have some sort of confidence in how well this model performs, or maybe how good this data quality is for my problem, you can sort of weight and combine them and sort of at least maybe improve performance, or sort of not degrade performance as much as would normally happen. Just to kind of wrap things up a little bit, limited and simulated data, can miss important features. You might not have enough images in your data set to kind of cover everything that you might expect to see in deployment. With simulated data, you often sort of simplify and lose some of those features and you see in real world data. This can make training deep learning models and models that are able to generalize a lot more difficult. I still think that fusion can improve performance in these scenarios, but you really have to understand which data sources are better than others, and then learning how do you deal with those, or maybe which models that you're trying to fuse together perform better or worse with the data that you have, and then knowing, which data sources do I rely on, or how do I develop a discount factor so I know which models I can be more confident in, that they're more reliable, and how do I weight those to get better performance. So thanks everyone for listening to my talk, and I'll open it now to any questions.
Thank you, Daniel. Um, Again, feel free to put questions in the Q&A. I actually have a question. So for the first instance where you're creating, I guess, data augmentations to help,
Mhm.
uh, my understanding from what you're seeing is that it may help in some areas, but with the S band particularly, it negatively impacts performance. Um, so does that give you any broader outlook into how to consider data augmentations, like what to determine makes a good augmentation? And do you have any intuition about why these specific ones worked poorly on the S band?
Yeah, so the augmentations were applied to the test data only. And so we're really trying to make the test data outside of the domain of training data. Right? So the assumption is that no matter how good we are at simulating this data, we're not going to be able to incorporate all the variations you see in the real world. And so we sort of do a proof of concept where we train on data that isn't augmented and then apply some augmentation to the test data, sort of artificially creating this gap between our training and deployment data, as to why the augmentations impact the different sources of data, the different SAR bands differently. I don't have a good answer for you. We have used this data set for a couple different types of studies. The S-band data source has just always been underperforming, and the C-band does really well. I think it has to do with the C-band models look really kind of crisp and easy to read, where S-band has some noise and stuff in it. I mean, X-band has some noise in it too. We've looked at it a bunch. I don't know if I have an idea of, just by looking at it or visual assessment, why it is. It's more we understand that C band does good and the S band does poorly just based on a bunch of tests and evaluation. And so I think that's kind of a little bit of my point, is like you don't really know what data source and model are going to work well until you start doing, training models and testing them, and maybe adding augmentations or creating hard test sets, where you're challenging this model a little bit. And you might say, oh, well, like C band isn't as brittle as S band is.
Next question is, in your evaluation on the test data, which I understand to be a mixture of original and generated data, what fraction of the S-band errors were occurring in real data versus generated data?
So all of the data that we've been using is generated data. Um, the example of real data that I showed was, isn't it, just to kind of compare the two, to show, what are we missing just by only simulating data. And there are other data sets. I know the rare planes one has a mix of real and simulated data as well. I think part of the reason the authors developed it was, how do we train on simulated and then transfer to real world? And they found that even though, I would say their simulated data looks more realistic than what we're dealing with, and they still struggle to sort of jump that gap.
Another question I had on the combination of the different models. Did you feel like the selection of models was chosen to provide diversity in how they may be performing and therefore increase the possibility of them improving when combined?
Yes, that was the goal. assuming we're referring to this one. Yeah, the goal was to take multiple sort of open source off the shelf models, fine tune them on this data set, and then combine the outputs. But the goal being, we don't have a lot of data, so we want something that's going to work with, kind of minimal effort in a sense. So we want to have um, models that might be able to deal with differences in flooding from, these two are the US and Germany, but if you wanted to deploy similar models in like South America or Africa or Asia, they're gonna have different features. Maybe you don't have as many, maybe you don't have like a large data set already of, pre and post floods in Asia. So you want to be able to like fine tune something and maybe combine a bunch of different models. Maybe you have one good model that works really well in Asia, and then you're going to combine it with one or two of these models here and kind of see if that helps, boost performance a little bit or like find some things that are going on. And we also found, it's more of an aside, but one of the benefits we found from data fusion as well is that we can calculate uncertainty between the two models. So, how much do these models differ, and what does that tell us about the performance, and how well the model's predicting?
Yeah, very interesting. If the underlying model is incorrect or data quality is poor, the fit is poor either way. Can you give examples where the model is found to be the culprit?
Yeah, so I think this example with the SpaceNet data set, the model is the culprit. So these three different models were all trained on the exact same data, and there's different performance between them. And we ended up using the discount factor to kind of help deal with that. Um, so what was the full question again?
I think it's just giving an example where the model
Okay.
is found to be the culprit.
Yeah, and I think that one's a little more difficult to deal with because then, I mean, one of the questions I had too was like, why bother keeping the YOLO model, in this at all? I think I was really surprised that using the discount factor kind of made up for that gap in performance. I would say that, that probably you would want to have a larger model testing and selection process going on to see, which models do I trust better? I think the YOLO model wasn't really well suited for this task. I think that's why it doesn't perform well, but I think kind of, maybe opening it up to a larger selection of models and maybe having more rubric or something to test and choose.